1964, a quiet physicist at CERN proved something that should have made front-page news in every country on Earth. His name was John Bell. His paper was 6 pages long, published in an obscure journal that paid its authors instead of charging them. And in those 6 pages, he demonstrated that reality is not what we think it is. Not in some hand-wavy philosophical sense. In a mathematical, testable, no way around it sense. Bell showed that quantum mechanics is incompatible with our most basic assumption about how the universe works. That assumption is called locality. The idea that what happens here, right now, cannot instantly affect what happens over there. That causes come before effects, that the past creates the present, and the present creates the future, and never ever the other way around. For 60 years now, experiment after experiment has confirmed that Bell was right. The universe violates his inequality. Reality does not play by the rules we assumed. And physicists have been arguing ever since about what that actually means. There are several ways out. You can accept it that particles somehow communicate across any distance instantaneously, violating Einstein's speed limit. You can accept that every quantum measurement splits the universe into parallel branches. You can accept that nothing is real until you look at it. Or you can accept the option most physicists don't even want to talk about. The option that is mathematically clean, experimentally consistent, and absolutely terrifying. You can accept that the future reaches back and shapes the past. This isn't science fiction. This is called retrocausality. And the case for it is stronger than you probably think. Let's start with the man who first made physicists comfortable with the idea that time might not work the way we assume. Not because he believed in backward causation, but because he asked questions so strange, so fundamental, that backward causation became one of the only coherent answers. John Archibald Wheeler was born on July 9th, 1911, in Jacksonville, Florida. Both his parents were librarians. He earned his PhD from Johns Hopkins University at 21 years old, then crossed the Atlantic to study under Niels Bohr in Copenhagen. By his mid-20s, he was already working at the frontier of nuclear physics. And then the war came. Wheeler joined the Manhattan Project, working at the Metallurgical Laboratory and later at the Hanford site in Washington State, where the plutonium for the first nuclear weapons was being produced. While he was there, his younger brother Joe was fighting in Italy. Joe sent him a postcard with just 2 words on it. Hurry up. Joe was killed in October 1944. Wheeler never got over it. He wrote later that he couldn't stop thinking about it and hadn't stopped thinking about it since, that the war could have been over in October 1944 if the bomb had been ready sooner, that his brother might have lived. Think about that for a second. A man who would spend the rest of his career asking whether the future can influence the past, carrying a grief rooted in the feeling that he hadn't been fast enough to change an outcome, that the timing of events, the sequence, the order of cause and effect was the thing that took his brother from him. I'm not saying that's why Wheeler eventually proposed the participatory universe, but I'm not saying it's unrelated either. After the war, Wheeler returned to Princeton, and in 1940, before the war had even started, something remarkable had happened there. Wheeler had picked up the phone and called his graduate student, a 22-year-old kid named Richard Feynman and said something that Feynman would remember for the rest of his life. "I know why all electrons have the same charge and the same mass," Wheeler told him. "Because they are all the same electron." Wheeler's idea was simple and insane. There is only one electron in the entire universe. It zigzags forward and backward through time, weaving through the fabric of space-time like a single thread through a vast tapestry. When it's traveling forward, we see an electron. When it's traveling backward, we see a positron. Every electron you've ever encountered, every electron in your body, in the sun, in distant galaxies, is the same particle making its way back and forth through history. Feynman didn't buy the full hypothesis. There were obvious problems with it. If every positron is just an electron going backward, there should be equal numbers of electrons and positrons in the universe, and there aren't. But Feynman took the core insight, the idea that antiparticles could be treated as particles moving backward through time, and built it into his Nobel Prize-winning work on quantum electrodynamics. The Feynman diagrams that every physics student learns to draw today include arrows going backward in time. They're usually treated as mathematical shorthand, but the mathematical shorthand keeps working, and nobody has been able to explain why it works so well if time is truly a one-way street. Wheeler and Feynman had already laid the groundwork together. In 1945 and 49, they published papers on something called absorber theory, a framework for electromagnetic radiation that treated advanced waves, waves traveling backward in time, as physically real and necessary. Their math showed that when a charged particle accelerates, it doesn't just send electromagnetic waves into the future. It also receives waves from the future, from every particle that will eventually absorb that radiation. The interaction between these forward and backward waves produces the radiation we actually observe. It was elegant, it was time-symmetric, and most physicists filed it under interesting mathematical curiosity and moved on. But Wheeler didn't move on. Wheeler never moved on from anything. The man coined more terms in physics than almost anyone in history. Black hole. He popularized that in 1967. Wormhole. Quantum foam. It from bit. He wrote on chalkboards with both hands simultaneously, twirling around to make eye contact with his students while equations appeared behind him as if by magic. And in 1978, at a symposium honoring the student he'd launched decades earlier, Wheeler proposed an experiment that would make the question of time's direction impossible to ignore. He called it the delayed choice experiment. Here's the setup. You have a single photon, a particle of light. You send it toward a beam splitter, which is basically a half-silvered mirror. The photon has a 50-50 chance of going through or bouncing off. If it goes through, it takes path A. If it bounces, it takes path B. Mirrors redirect both paths so they converge at a single point. Now, at that convergence point, you have a choice. You can put a second beam splitter there, or you can leave it empty. If you insert the second beam splitter, the two paths recombine. The photon interferes with itself, producing an interference pattern. This is wave behavior. The photon traveled both paths simultaneously, like a wave. If you remove the second beam splitter, detectors at the end of each path simply click or don't click. You find out which path the photon took. This is particle behavior. The photon went one way or the other, like a bullet. Nothing strange so far. This is just the double-slit experiment, dressed up with mirrors. We've known since the 1920s that quantum objects behave as waves when you don't look at which path they take, and as particles when you do. But here's Wheeler's twist. What if you make the choice, insert or remove the second beam splitter after the photon has already passed the first one? The photon hits the first beam splitter. It either goes through or bounces. It's traveling along one path or both paths, or whatever it does in between measurements. And we'll get to why whatever it does matters enormously. While the photon is in flight, you decide beam splitter in or beam splitter out. If you put it in, you get interference. The photon behaved as a wave, both paths. If you leave it out, you get a click at one detector. The photon behaved as a particle, one path. But you made that decision after the photon had already chosen what to do at the first beam splitter, after it had already entered the apparatus and started traveling. Your choice now seems to determine what the photon did then. Wheeler put it this way: it is wrong to attribute a tangibility to the photon in all its travel, from the point of entry to its last instant of flight. The photon doesn't have a definite wave or particle nature until measurement defines it, and that measurement can come after the photon's journey has already begun. This was a thought experiment in 1978. It took almost 30 years to actually do it properly. In 2007, a team led by Vincent Jacques, and including Alain Aspect, the same physicist who would later win the Nobel Prize, published the results in Science. They used a single photon source based on a nitrogen vacancy center in diamond and an electro-optical modulator that could switch configurations in nanoseconds. The switch happened while the photon was in flight, ensuring that the choice was made after the photon had entered the interferometer. There was no way for information about the choice to reach the photon in time. The results matched quantum mechanics perfectly. 94% interference visibility when the second beam splitter was inserted, less than 1% error in path detection when it was removed. The photon's behavior was determined by a choice made after the photon was already traveling. But wait, it gets stranger. Wheeler proposed a cosmic version. Imagine light from a distant quasar, billions of light years away. That light passes a massive galaxy on its way to Earth, and the galaxy's gravity bends the light, creating two paths around the galaxy. This is gravitational lensing, and it really happens. We've observed it. Now, an astronomer on Earth can choose how to observe that light. Set up your telescope one way, and you see interference, both paths. Wave behavior. Set it up another way, and you detect which path the light took. Particle behavior. The light has been traveling for billions of years. The photon left that quasar when Earth didn't even exist yet. And your choice, right now, today, seems to determine what that photon did billions of years ago, whether it took one path around the galaxy or both. In 2017, a team at MIT and the University of Vienna actually tested a version of this. They didn't use quasars for the beam splitter decision, but they did use starlight from stars 600 light years away to determine their detector settings. The idea was to push back the moment at which any hidden variable could have been set. If some cosmic conspiracy is pre-arranging the outcomes, that conspiracy would have had to be in place 600 years ago before the starlight left those stars. The quantum predictions held. The correlations were exactly what quantum mechanics said they'd be. Then in 2018, another team went further. They used photons from quasars billions of light years away to set their detector configurations. Any hidden variable conspiracy would have to stretch back to near the beginning of the universe itself. Same result. Quantum mechanics wins again. Now, I need to be honest about something here, because this is where a lot of YouTube videos get it wrong. The delayed choice experiment, by itself, does not prove retrocausality. There are perfectly good interpretations of quantum mechanics that explain these results without anything traveling backward in time. In the many worlds interpretation, for example, the photon is always in superposition, always in both paths. A measurement just reveals which branch of the universal wave function you end up in. No backward causation needed. The photon didn't choose to be a wave or particle in the past. It was both always, and your measurement just determined which aspect you observed. As physicist Sean Carroll puts it, there's no need to invoke retrocausality to explain the delayed choice experiment. The photon remains in superposition throughout. Measurement simply reveals different aspects of that superposition. So if the delayed choice experiment doesn't prove retrocausality, why are we talking about it? Because it establishes something crucial. It establishes that our intuitive picture of time, the picture where the photon makes a decision at the first beam splitter and then sticks with it, is wrong. The photon does not have a definite history until you define what counts as a measurement. The past, at the quantum level, is not fixed until something in the present or the future pins it down. That doesn't mean the future causes the past, but it means the past isn't what we thought it was. It's not a done deal. It's not carved in stone. It's more like a story that hasn't been fully written yet, and later events get to fill in earlier chapters. Wheeler had a beautiful metaphor for this. He called it the Great Smoky Dragon. Imagine a dragon. Its tail is sharp and clear where the photon begins its journey. Its mouth is sharp and clear where the photon hits the detector. But the body of the dragon, the part in between, is covered in impenetrable smoke. You can't see through it. You can't peel it away. You have no right to say what the dragon looks like in between those two sharp points. The universe, Wheeler was saying, doesn't have a definite middle. It has definite beginnings and definite endings, at least at the quantum level, and the stuff in between is smoke. And if the stuff in between is smoke, then talking about whether causes come before effects starts to lose its meaning, because before and after require a clear sequence of events, and the dragon's body has no clear sequence. It has no clear anything. Wheeler went even further. He proposed what he called the participatory universe. Not that consciousness creates reality, which is a common misreading of his idea, but that the universe doesn't have definite properties until something, some physical interaction, some measurement defines them. And those measurements don't just reveal what's already there. They participate in bringing reality into being. We are participators, Wheeler wrote, in bringing into being not only the near and here, but the far away and long ago. Read that again. Not just the near and here, the far away and long ago. If Wheeler is right, then when that astronomer points a telescope at quasar light that's been traveling for 12 billion years and chooses how to measure it, that choice participates in defining what happened 12 billion years ago, not by sending a signal backward, not by changing the past in any way that could create a paradox, but by filling in a detail that was never defined until now, by writing a sentence in a chapter that was left blank until someone, 12 billion years later, finally put pen to paper. Wheeler illustrated this with a game he called Negative 20 Questions. The normal game has 20 questions, and someone has secretly chosen an object, and you try to figure out what it is. In Wheeler's version, nobody has chosen anything. The respondent doesn't have an object in mind. They just answer each question consistently, yes or no, making sure they don't contradict any previous answer. By the end, an object emerges from the pattern of answers, but it was never pre-selected. It was created by the process of asking. Reality, Wheeler suggested, works the same way. This was 1978. Wheeler was 67 years old. He'd spent his entire career at the center of physics, had worked on the bomb, had mentored Feynman, had named black holes, had been present for or contributed to nearly every major development in 20th century theoretical physics. And at the end of all that, this was his conclusion. That reality is participatory, that the universe does not exist independent of observation, that the past is not fully real until the present makes it so. Stephen Hawking called Wheeler the hero of the black hole story. But Wheeler's deepest contribution might not have been to astrophysics at all. It might have been to the nature of time, because Wheeler's delayed choice experiment, even though it doesn't prove retrocausality on its own, opens a door. And once that door is open, you start noticing things. You start noticing that the same experiments that seem to dissolve the past also seem to connect the future to the past in ways that can't easily be explained away. And that's where things get genuinely unsettling. Because in 1964, the same year Wheeler's future collaborators were beginning to formalize time-symmetric quantum mechanics, a man in Belfast was about to prove something that would take the physics world decades to fully absorb. John Bell was about to demonstrate that quantum mechanics requires something impossible. And one of the only clean ways to explain that impossibility is to accept that the future is already reaching back, right now, shaping the present from a direction we can't even point to. But to understand what Bell proved and why it terrified him, we need to talk about socks. Reinhold Bertelsmann was a physicist at CERN in the 1970s and 80s. He had a peculiar habit. Every day, he wore mismatched socks. One pink, one not pink, one green, one not green. Never a matching pair. His colleague John Bell found this endlessly amusing, and in 1981, Bell wrote a paper that opened with the following observation. If you see one of Bertelsmann's socks and it's pink, you instantly know the other sock is not pink. This seems like a mystery, like information has traveled instantaneously from one sock to the other. But it isn't mysterious at all. Bertelsmann chose his socks in the morning. The correlation was set at the source. No signal needed to travel between the socks. This, Bell explained, is how most people want to think about quantum entanglement. Two particles are created together. They fly apart. You measure one and instantly know something about the other, even if the other is on the far side of the galaxy. Einstein called this spooky action at a distance and insisted it must work like Bertelsmann's socks. The particles carry hidden instructions from the moment they're created, predetermined answers to any question you might ask, like socks with their colors already chosen. Einstein was wrong. Bell proved it, mathematically, rigorously, and in a way that could be tested in a laboratory. His 1964 paper, published in that obscure journal that paid its authors, contained a set of inequalities, limits on how strongly the measurements of two distant particles can be correlated if those particles carry predetermined instructions. If reality works like Bertelsmann's socks, where properties exist before measurement and no signal passes between particles, then a particular quantity, later formalized as S in the CH-SH inequality, cannot exceed 2. Quantum mechanics predicts it can reach 2 times the square root of 2, roughly 2.828. That might sound like a small difference, 2 versus 2.8. But it's not small. It's the difference between a universe where the past fully determines the future and a universe where something much stranger is happening. It's the difference between socks and sorcery. And for 17 years after Bell published his paper, nobody tested it. Part of the reason was practical. The experiments are incredibly difficult. You need to create pairs of entangled particles, send them to distant detectors, measure their properties at precisely chosen angles, and do this thousands of times with enough statistical rigor to rule out coincidence. In the 1960s and 70s, that was barely within reach of the best labs in the world. But part of the reason was cultural. Quantum foundations, the study of what quantum mechanics actually means, was considered career poison. The Copenhagen interpretation, championed by Niels Bohr, said the question was meaningless. Shut up and calculate, as the saying went. Don't ask what the equations mean. Just use them. Bell didn't listen. John Stuart Bell was born on July 28, 1928, in Belfast, Northern Ireland, to a working-class Protestant family. Money was tight. Neither of his parents completed high school. None of his siblings did either. But John decided at age 11 that he wanted to be a scientist, and his family supported him as best they could, scraping together money for books and school fees. He earned degrees in experimental and mathematical physics from Queen's University Belfast, then a PhD from the University of Birmingham under Rudolf Peierls. In 1960, he joined CERN in Geneva with his wife, Mary Ross Bell, who was also a physicist. His official job was designing particle accelerators and doing calculations for high-energy experiments. Quantum foundations was his hobby, something he worked on during evenings and vacations, something he couldn't stop thinking about, even though the physics establishment had declared the questions he was asking to be unscientific. And in 1964, during a sabbatical leave, he wrote the paper that changed everything. What Bell showed was this. Imagine you have 2 entangled particles. You send them to 2 distant laboratories. In each laboratory, an experimenter independently chooses a measurement direction. Call them setting A and setting B. They can choose from several different directions. They measure their particle and record the result. If the particles carry predetermined instructions, if they left the source with a fixed set of hidden variables telling them how to respond to any measurement, then the correlations between the 2 laboratories' results are limited. Bell derived the mathematical limit. It's an inequality, and quantum mechanics predicts that entangled particles violate it. The crucial word is independently. The proof assumes that the measurement choices in laboratory A are independent of the hidden variables carried by the particles, and vice versa. Physicists call this measurement independence or statistical independence. Mathematically, it means the probability of the hidden variable lambda, given the measurement setting alpha, equals the probability of lambda on its own, p of lambda, given alpha equals p of lambda. Remember that assumption. We're going to come back to it, because the entire retrocausality debate hinges on what happens when you drop it. The first real test came in 1972, when John Clauser and Stuart Friedman at UC Berkeley measured correlations between entangled photons and found a violation of Bell's inequality by over 6 standard deviations. That's a 1 in a billion chance of being a statistical fluke. But the definitive experiments came from a young French physicist named Alain Aspect. Aspect was doing his PhD thesis at the Institut d'Optique in Orsay, France, and he decided to stake his entire career on testing Bell's inequality. In 1975, before starting his experiments, he traveled to Geneva to discuss his plans with Bell himself. He was nervous. He half expected Bell to tell him the experiment was pointless, or that someone had already done it properly. Instead, Bell asked him a single question. "Do you have tenure?" Aspect didn't. Bell wished him good luck. Not because the experiment wasn't worth doing, because it might end Aspect's career even if it worked. Quantum foundations was that unfashionable. Aspect ran 3 progressively more refined experiments between 1981 and 1982. The first 2 used increasingly sophisticated photon sources and polarization measurements. The results were striking. His January 1982 experiment achieved a Bell parameter, that S value, of 2.697, plus or minus 0.015. The classical limit is 2. He was nearly 7/10 above it, with a margin of error so small it amounted to a violation of more than 40 standard deviations. 40 standard deviations. To put that in perspective, the Higgs boson discovery at the Large Hadron Collider, which made headlines around the world and won a Nobel Prize, was announced at 5 standard deviations. Aspect had 8 times that level of certainty, and almost nobody outside of physics noticed. But it was Aspect's 3rd experiment, published in December 1982, that really mattered, because in this version, he used acousto-optical switches running at about 50 megahertz to change the measurement settings, while the photons were in flight. The photons were already traveling toward the detectors when the decision was made about what to measure. This closed what's called the locality loophole, the possibility that one detector could somehow signal to the other what it was measuring, and the particles could adjust their behavior accordingly. With the switches in place, the violation dropped to 5 standard deviations, still overwhelming, still impossible under local hidden variables. But now, with the assurance that no light speed signal could have coordinated the results. The thing about Bell's theorem, though, is that it doesn't have just one loophole. It has several. The locality loophole asks whether the detectors could have communicated. The detection loophole asks whether the detectors missed enough particles to bias the results. The freedom of choice loophole asks whether the measurement settings were truly random. For decades, Every experiment closed some loopholes, but left others open. Skeptics, and there were always skeptics, could always point to a remaining gap. That changed in 2015. In October 2015, a team in Delft, the Netherlands, led by Ronald Hansen, published a paper in Nature describing the first loophole-free Bell test. They used nitrogen vacancy centers in diamond, one at each end of their campus, separated by 1.3 kilometers. Over 220 hours spread across 18 days, they accumulated 245 usable trials. The S value came out to 2.42, plus or minus 0.20. The P value, the probability of getting this result by chance, was 0.039. The same month, two more teams published loophole-free results. A Vienna group led by Marissa Giustina used polarization-entangled photons in the sub-basement of the Hofburg Imperial Palace, with detectors 58 meters apart and superconducting sensors achieving over 75% efficiency. Their p-value was less than 1 in a million. And a NIS Boulder team, led by Lyndon Schalm, achieved the most statistically devastating result of all: 185 meters of separation, a p-value of approximately 3.74 times 10 to the negative 31st power. That is 11.5 standard deviations. The probability of this result occurring by chance is so small that you would need to run the experiment more times than there are atoms in the visible universe before you would expect to see it happen once as a fluke. By the end of 2015, it was over. Every loophole had been closed simultaneously. The universe really does violate Bell's inequality. Local hidden variables, Bertelmann's socks. Einstein's hope that quantum mechanics was just concealing a sensible, local, deterministic reality. All of it was dead. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alan Aspect, and Anton Zeilinger for exactly this work. During the ceremony, Aspect said something that stayed with me. He said this recognition should go first to the late John Stuart Bell, without whom none of them would have been there. Bell never saw it. He died of a cerebral hemorrhage on October 1st, 1990, at 62 years old. His death was sudden and unexpected. The Nobel Committee would have considered his work the following year. Quantum foundations, the field he'd been told would ruin his career, was about to become the most exciting frontier in physics. He missed it by months. But here's what Bell understood better than almost anyone. His theorem doesn't just kill local hidden variables. It kills any theory that combines two things: locality and measurement independence. You must give up at least one. Giving up locality means accepting that distant particles can influence each other instantaneously. This is spooky action at a distance. Most physicists have grudgingly accepted some version of this, even though it sits uncomfortably with relativity. But there's another option. You can keep locality. You can keep everything happening at light speed or slower. You can have a perfectly relativistic, perfectly respectable theory. You just have to give up measurement independence. And that is where retrocausality enters the picture. Measurement independence sounds technical, but the idea is simple. It means your choice of what to measure is not correlated with the properties of the thing you're measuring. When you decide to check the polarization of a photon at a certain angle, that decision has nothing to do with the hidden variables the photon is carrying. Your choice is free. The The particle's properties are set. The two are independent. This seems so obvious that most physicists never even think about it. Of course, your measurement choice is independent. You could flip a coin. You could use a random number generator. You could base it on the last digit of the stock price of a random company. How could the photon possibly know in advance what you're going to measure? But Bell's theorem requires this assumption. If measurement independence fails, if the particle's hidden variables are somehow correlated with your future choice of what to measure, then the math changes. The inequality doesn't hold, and quantum mechanics can be explained without any spooky action at a distance. There are exactly two ways to violate measurement independence. Two ways the particle's past could be connected to your future choice, and they lead to radically different pictures of reality. The first way is superdeterminism. This is the idea that everything, including your choice of measurement setting, was determined at the Big Bang. There is no free choice. There was never any free choice. The initial conditions of the universe were set up in exactly the right way, so that whenever you decide to measure a photon's polarization, your decision was always going to correlate with the photon's hidden variables, not because of any causal connection between them, but because both were inevitable consequences of the same initial conditions 13.8 billion years ago. Gerard 't Hooft, who won the Nobel Prize in 1999 for his work on the Standard Model, is probably the most prominent advocate of superdeterminism. His argument is straightforward. The entire universe started with a single Big Bang. Everything in our universe shares a common past. So, of course, things are correlated. Everything is correlated with everything else if you trace it back far enough. Sabine Hossenfelder, a theoretical physicist at the Munich Center for Mathematical Philosophy, has championed the same idea, calling it a promising approach not just for explaining Bell violations, but for solving the measurement problem entirely. But superdeterminism has a problem, a big one. If your measurement choices are predetermined, then experimental science itself becomes suspect. How do you test a theory if the universe can rig your experiments? How do you trust any result if the settings on your detectors were chosen not by you, but by the initial conditions of the cosmos? Anton Zeilinger, one of the 2022 Nobel laureates, put it bluntly. If superdeterminism were true, he said, it would make no sense at all to ask nature questions in an experiment, because nature could determine what our questions are. That's a price most physicists aren't willing to pay. But there's a second way to violate measurement independence. Instead of saying the past determines your future choices, you can say, your future choices influence the past. The particle's hidden variables aren't correlated with your measurement setting because of shared ancient history. They're correlated because your choice, when you make it, reaches backward and shapes the hidden variables the particle was carrying all along. That's retrocausality. And here's what makes it different from superdeterminism, and why an increasing number of physicists find it more palatable. Retrocausality doesn't eliminate free will. You genuinely choose your measurement setting. Nobody and nothing predetermined it. But that free choice, once made, has consequences that propagate backward through time, subtly adjusting the hidden variables of the particle to create the correlations that Bell's theorem says must exist. You choose freely, and the universe rearranges its past to accommodate your choice. If that sounds insane, I understand. But mathematically, it works. It preserves locality. It's consistent with special relativity. It doesn't require faster-than-light signals, and it avoids the philosophical nightmare of superdeterminism, where science itself loses its foundation. The question is whether anyone saw this coming, and the answer is yes. Someone saw it coming in 1953, more than a decade before Bell even published his theorem. And almost nobody listened. Olivier Coste de Beauregard was a French physicist born in 1911, the same year as Wheeler. He studied under Louis de Broglie, one of the founding figures of quantum mechanics, the man who first proposed that particles have wave properties. And in 1953, Coste de Beauregard proposed something that de Broglie found so outrageous that he initially forbade its publication. Coste de Beauregard's insight was about the EPR paradox, the thought experiment that Einstein, Podolsky, and Rosen had published in 1935 to argue that quantum mechanics was incomplete. In the EPR scenario, two particles are entangled and then separated. Measuring one instantly reveals information about the other, no matter how far apart they are. Einstein argued this proved that the particles must carry hidden variables, predetermined answers, because the alternative, that measuring one particle instantaneously affects the other across arbitrary distances, violated relativity. Coste de Beauregard saw a third option. What if the correlation between the two distant particles was established not through space, but through time? His proposal was what we now call zigzag causation. When you measure particle A, that measurement sends a causal influence backward in time, along particle A's world line, to the moment when the two particles were created together. At that shared origin point, the influence crosses over to particle B's world line and then travels forward in time to particle B's detector. The influence never has to travel faster than light. It never violates relativity. It just takes a detour through the past. Picture it like a letter. You can't teleport a letter from New York to London instantaneously, but you can send it backward in time to a moment when New York and London were at the same point, when the postal worker hadn't yet left the sorting office, and then let it travel forward along a different route. The total path is longer, but it never requires anything to move faster than light at any point along the way. Coste de Beauregard's idea was ignored for decades, partly because it sounded crazy, partly because de Broglie, his mentor, had suppressed it, and partly because, in 1953, nobody had yet proven that hidden variables couldn't explain quantum mechanics. Bell's theorem was still 11 years away. There was no reason to reach for something as radical as backward causation, when simpler explanations hadn't yet been ruled out. But after Bell, after aspect, after the loophole-free tests, the simpler explanations were ruled out, and Coste de Beauregard's zigzag started looking less crazy and more prescient. Here's the remarkable thing. Coste de Beauregard lived long enough to see his ideas vindicated, at least as a serious possibility. He died in 2007, at 96 years old, and in one of those beautiful ironies of scientific history, his student Alain Aspect, the man he had discussed these ideas with, won the Nobel Prize for the very experiments that made retrocausality a viable explanation for quantum non-locality. Costa de Beauregard once wrote that since EPR correlations are very well validated experimentally, and the phenomenon itself is crazy, any explanation of it must be crazy too. He was joking, but he was also right. The universe is not normal, and the explanations that fit it best are the ones that give up trying to be normal. But Costa de Beauregard's proposal was more of a sketch than a theory, a direction, not a destination. The first person to build a rigorous mathematical framework in which the future genuinely shapes the past was a physicist working in Israel, and he's still alive, still publishing papers, still, at 93 years old, insisting that the future is just as real as the past and just as capable of leaving its fingerprints on the present. His name is Yakir Aharonov. Aharonov was born on August 28, 1932, in Haifa, in what was then the British Mandate of Palestine. He studied physics at the Technion, then moved to Bristol to work under David Bohm, one of the most original and underappreciated minds in 20th century physics. And in 1959, Aharonov and Bohm published a paper that broke physics open. The Aharonov-Bohm effect demonstrated something that should have been impossible under the classical understanding of electromagnetism. They showed that a magnetic field confined to a small region, completely shielded from the outside world, could still affect the behavior of electrons passing by outside the shield. The electrons never enter the field. They never experience any electromagnetic force, but their quantum behavior changes depending on the magnetic flux inside the shielded region. This was deeply unsettling. In classical physics, fields exert forces, and forces change particle trajectories. No field, no force, no effect. But Aharonov and Bohm showed that in quantum mechanics, the electromagnetic potential, a mathematical quantity that classical physicists treated as a convenient fiction, has direct physical consequences. The thing everyone thought was just a bookkeeping tool turned out to be more fundamental than the forces themselves. The physics community was initially skeptical. Some flatly denied the effect was real, but experiment after experiment confirmed it. Most definitively, Akira Tonomura's 1986 electron holography experiments and the Aharonov-Bohm effect is now a cornerstone of quantum mechanics. Why does this matter for retrocausality? Because Aharonov had learned a lesson. The quantities physicists dismiss as mathematical conveniences might be telling us something real about nature. The formalism might be smarter than the physicists interpreting it. And in 1964, the same year Bell published his theorem, Aharonov applied that lesson to time. Working with Peter Bergman, one of Einstein's former assistants, and Joel Lebowitz, Aharonov published a paper titled Time-Symmetry in the Quantum Process of Measurement. The central argument was this: standard quantum mechanics describes a system using a state vector that evolves forward in time. You start with initial conditions, apply the equations, and predict what happens next. The past determines the future. Simple, but the equations of quantum mechanics are time-symmetric. They work just as well backward as forward. So why do we only use forward evolving state vectors? Why don't we also use a state vector that evolves backward from the future? Aharonov's answer was that we should. The result is called the Two-State Vector Formalism, or TSVF. In this framework, The complete description of a quantum system at any moment requires two state vectors, one evolving forward from past boundary conditions, and one evolving backward from future boundary conditions. The present is shaped by both. Think about what that means. In standard quantum mechanics, the state of a particle right now depends only on what happened before. In Aharonov's framework, the state of a particle right now depends on what happened before and what will happen later. The future has a vote. Aharonov proposed that the universe might have what he called a destiny state, a final boundary condition that reaches back through time to constrain the present. Not in a way that predetermines everything. The forward state and the backward state together create probabilities, not certainties. Quantum uncertainty is preserved. Free will is preserved. But the future participates. He told Discover magazine that nature is trying to tell us something, that there is a difference between two seemingly identical particles with different fates. But that difference can only be found in the future. Two particles, prepared identically, measured identically, occupying the same quantum state as far as any forward-looking description can tell. But one of them is destined to be measured one way, and the other is destined to be measured a different way. And if you look closely enough, using the right kind of measurement, you can already see the shadow of that future difference in the present. This led Aharonov to his most startling contribution. In 1988, with David Albert and Lev Vaidman, he introduced the concept of weak measurements and weak values. The paper's title gives away the punchline: how the result of a measurement of a component of the spin of a spin 1/2 particle can turn out to be 100. Spin 1/2 particles can normally only give measurement results of +1/2 or -1/2. That's it. Those are the only options. It's like asking someone to pick a number between 0 and 1, and the only answers allowed are 0 or 1. There is no in-between, and there is certainly no 100. But Aharonov showed that if you measure very gently, barely disturbing the system, and then post-select, meaning you only keep the results where the particle later ends up in a specific state, the average value of your gentle measurement can be wildly outside the normal range. You can get 100. You can get -1,000. You can get any number at all. These are called weak values, and they've been confirmed experimentally many times over, with amplification factors exceeding 10,000 demonstrated in laboratory settings. They're not just mathematical curiosities. They're used in precision measurement technology, in quantum optics, and in fundamental tests of quantum mechanics. But the philosophical implications are staggering. A weak value depends on both the initial state of the system, which is set in the past, and the post-selected state, which is set in the future. It is, in a very real sense, a quantity determined by the future as much as the past. And if you take the two-state vector formalism seriously, if you believe it's telling us something about reality and not just about our calculations, then weak values are the shadow of the future reaching back into the present. Aharonov has a way of resolving the apparent paradox between retrocausality and free will that I find beautiful. He quotes Rabbi Akiva, a first-century sage who said, "All is foreseen, but freedom of choice is given." His explanation is this: the future does influence the past. But quantum uncertainty prevents you from ever using that influence to create a paradox. You can see the future's fingerprints in statistical patterns, in weak values, in the correlations between entangled particles. But you can never see them in any single event. Individual outcomes remain unpredictable. The signal is hidden in the noise. The future writes in invisible ink that only becomes legible when you gather enough data and look at the statistics. This is why retrocausality doesn't let you build a time machine or send a message to your past self. The no communication theorem, proven by Philippe Eberhard in 1978 and expanded in 1988, demonstrates that no classical information can be transmitted faster than light or backward in time through quantum entanglement. The future can reach back, but only in ways that average out, that cancel, that hide their own influence from any individual observer. Aharonov received the Wolf Prize in Physics in 1998 and the National Medal of Science from President Obama in 2010. He was elected to the Royal Society of London as recently as 2024 at 92 years old. He is still publishing, still thinking about time, still insisting that the distinction between past and future is not what we assume. Now, right around here is where I need to address the elephant in the room. You may have heard of an experiment called the delayed choice quantum eraser. It's one of the most discussed experiments in popular physics. Dozens of YouTube videos claim it proves the future can change the past. Some of them have millions of views. They're wrong, and it's important to understand why they're wrong, because it clarifies what retrocausality actually is and isn't. The experiment was published in 2000 by Yoon-Ho Kim, R.U., S.P. Kulik, Y.H. Shi, and Marlon Scully. Here's what happens. A laser hits a special crystal and produces pairs of entangled photons. One photon, called the signal photon, goes to a detector screen. The other, called the idler photon, goes through a series of beam splitters to one of 4 other detectors. 2 of those detectors, D3 and D4, preserve witch path information. They tell you which slit the photon pair came from. The other 2, D1 and D2, erase witch path information by combining the paths at a final beam splitter. Here's the key. The idler photon's path is 2.5 meters longer than the signal photon's path. So the idler photon arrives at its detector about 8 nanoseconds after the signal photon has already hit the screen. The choice to erase or preserve witch path information happens after the signal photon has already been detected. When you look at the signal photon detections that coincided with D1 or D2, the erasure detectors, you see an interference pattern. When you look at the ones that coincided with D3 or D4, the witch path detectors, you see no interference. It looks like the idler photon's future measurement retroactively determined whether the signal photon produced an interference pattern or not. But here's what almost every popular explanation gets wrong. If you look at all the signal photon detections together, without sorting by idler detector, there is no interference pattern. None. Just a smooth blob. The interference only appears when you filter the data after the fact, using the idler photon results to sort the signal photon results into subsets. This means you cannot see any effect at the signal detector until after you've received the idler detector results and done the sorting. And receiving those results requires ordinary, classical, slower-than-light communication. You can't use this to send a message backward in time. You can't see the interference until after the classical data arrives. Physicist Johannes Fankhauser showed in 2019 that the quantum eraser is essentially a Bell-type scenario in which the resolution is rather trivial. The idler measurement doesn't create the interference pattern. It sorts pre-existing data into subsets that reveal hidden correlations. The correlations were always there. The sorting just makes them visible. Ruth Kastner's paper in Foundations of Physics the same year made the point even more directly. Her title said it all. The delayed choice quantum eraser neither erases nor delays. So, the quantum eraser doesn't prove retrocausality, but it does demonstrate something that connects to everything we've been discussing. The data at the signal detector contains more structure than you can see by looking at it directly. That hidden structure is only revealed by correlating it with measurements that happen later. The information was already there, encoded in the entanglement, but it took a future event to make it visible. This is exactly what Aharonov's framework predicts. The present contains information about the future, but that information is hidden. It's written in invisible ink. You can only read it by knowing the future measurement results, which is to say, you can only read it after the future has actually happened. The quantum eraser doesn't prove retrocausality, but it's consistent with it, and it demonstrates the exact kind of hidden temporal structure that retrocausal theories predict. Now, the quantum eraser isn't the only experiment that seems to blur the line between past and future. In 2012, a team led by Xiaosong Ma, working with Anton Zeilinger's group at the University of Vienna, published a result in Nature Physics that is harder to explain away. The experiment is called delayed choice entanglement swapping, and it realizes a thought experiment proposed by Asher Peris in 2000. Here's what happens. You create two pairs of entangled photons. Call them photons 1, 1 and 2 from the first pair, and photons 3 and 4 from the second pair. Photons 1 and 4 are sent directly to detectors and measured. Their polarization is recorded. Done. Finished. Those results are in the books. Photons 2 and 3 are sent through optical fiber delays, adding about 104 meters of extra path, which translates to about 350 nanoseconds of delay. After that delay, a quantum random number generator makes a choice. It decides whether to perform a Bell state measurement on photons 2 and 3, which entangles them with each other, or to measure them individually. Here's the thing. If the Bell state measurement is performed on photons 2 and 3, then photons 1 and 4 become entangled. They show quantum correlations, violating Bell's inequality, even though they were never entangled before, even though they came from different pairs that had no connection to each other. And if photons 2 and 3 are measured individually instead, then photons 1 and 4 show no entanglement at all. They behave like completely independent particles, but photons 1 and 4 were already measured 520 nanoseconds before the choice was made. Their results are already recorded, already in the computer, already, in a very real sense, part of the past, and yet the choice made 520 nanoseconds later determines whether those already recorded results show entanglement or not. The team reported a violation of the entanglement witness by 4.7 standard deviations. The statistics are clear. The choice made after photons 1 and 4 cease to exist determines the correlations between them. The authors describe this as quantum steering into the past. If you believe the quantum state is real, if you believe it describes something about the actual physical world and not just our knowledge of it, then what happened is that a future measurement retroactively created entanglement between two particles that had already been detected and destroyed. This is not the same as the quantum eraser. In the quantum eraser, the effect is invisible without post-selection, and the total data always shows no interference. In entanglement swapping, the total data for photons 1 and 4 genuinely changes statistical character depending on what happens to photons 2 and 3 later. The correlations are real, detectable, and contingent on a future event. Now, can you use this to send a message backward in time? No. The no communication theorem still holds. The change in correlations only becomes visible when you compare the results with the information about what choice was made for photons 2 and 3. You still need that classical data transfer. No paradoxes, no time travel. But the ontological implications are staggering. If the quantum state is physically real, then the reality of what photons 1 and 4 did was not settled when they were detected. It was settled later, by a measurement on different particles entirely. The past was rewritten, not in a way anyone could exploit, not in a way that creates contradictions, but rewritten nonetheless. By the time the entanglement swapping experiment was published, retrocausality had a fully developed theoretical framework waiting for it. Actually, it had two. The first was Aharonov's Two-State Vector Formalism, which we've already discussed. In TS-VF, the entanglement swapping result makes perfect sense. The backward evolving state from the future, Bell state measurement, reaches back to the moment the photons were created, adjusting the quantum description of photons 1 and 4. No spooky action at a distance needed, just ordinary causation, traveling in an unusual direction. The second framework was John Cramer's Transactional interpretation, published in Reviews of Modern Physics in 1986, and where Aharonov's approach is mathematically elegant, Cramer's is viscerally beautiful. John Gleason Cramer Jr. was born on October 24, 1934, in Houston, Texas. He earned all three of his physics degrees from Rice University and joined the University of Washington in 1964, where he spent his entire career. His day job was nuclear physics, specifically ultra-relativistic heavy ion collisions at CERN and Brookhaven National Laboratory. His side project was reimagining the foundations of quantum mechanics from the ground up. Cramer's transactional interpretation explains quantum phenomena through what he calls transactions, handshakes between the past and the future. When a source emits a photon, it sends out an offer wave that propagates forward through time. This is the ordinary quantum wave function, the one you would learn about in any physics class. But simultaneously, every potential absorber of that photon, every atom, every detector, every surface that could eventually capture it, sends back a confirmation wave that propagates backward through time. The offer wave travels into the future. The confirmation wave travels into the past. Where they overlap and reinforce each other, a transaction is completed. Energy, momentum, and angular momentum are exchanged. A photon is emitted here, absorbed there, everything conserved, everything consistent. Cramer built this on the Wheeler-Feynman absorber theory. The framework Wheeler and Feynman had developed in the 1940s for classical electrodynamics. But Cramer applied it to quantum mechanics, and the result was a complete interpretation that handles the double-slit experiment, entanglement, delayed choice, and every other quantum phenomenon without collapsing wave functions, without parallel universes, and without spooky action at a distance. The cost? You have to accept that waves travel backward in time. Cramer had a gift for vivid description. He wrote that when you stand in the dark and look at a star 100 light-years away, not only have the retarded light waves from the star been traveling for 100 years toward your eyes, but also advanced waves from your eyes have reached 100 years into the past to encourage the star to shine in your direction. Read that again slowly. Waves from your eyes, reaching 100 years into the past, encouraging a star to emit light toward the point where you will eventually be standing, looking up. You, tonight, looking at the sky, are sending a signal backward through a century of time, and the star 100 years ago is responding to it. That's either poetry or physics. Cramer would say it's both. He wasn't content to leave it as theory either. Between 2007 and 2014, Cramer actually tried to test whether quantum non-locality could be harnessed for backward-in-time signaling. He raised $40,000, partly through early crowdfunding, and collaborated with colleagues at the University of Washington and the University of Vienna. The experiments were painstaking and, ultimately, negative. Nature, Cramer concluded, appears to be well protected from the possibility of non-local signaling. For every interference pattern that might carry a signal, nature superimposes an anti-interference pattern that cancels it out. But this failure was actually a success in disguise. It confirmed that the transactional interpretation, with its backward-in-time waves, is consistent with the no-signaling constraint. The future does influence the past, but it does so in a way that can never be exploited for communication. The backward waves are there. They're real, or at least as real as anything in quantum mechanics. But they conspire, always and exactly, to prevent paradoxes. Cramer was also a science fiction novelist. He published 3 hard SF novels and wrote over 212 popular science columns for Analog magazine. The transactional interpretation, he once said, was the physics framework he'd most want to live in, because it meant the universe was participating in a continuous conversation between past and future, offer and confirmation, question and answer, a handshake across time. He's still alive as of this recording, 91 years old, still Professor Emeritus at the University of Washington, still thinking about time. So by the mid-2010s, the pieces were in place. Bell's theorem had shown that reality must be either non-local or measurement-dependent. Loophole-free experiments had confirmed the violations beyond any reasonable doubt. The cosmic Bell tests had pushed any hidden variable conspiracy back 600 years, then billions of years. The entanglement swapping experiment had demonstrated what looked like backward-in-time steering, and 2 independent theoretical frameworks, Aharonov's TSVF and Cramer's transactional interpretation, had shown that retrocausality was not just hand-waving, but rigorous, predictive physics. What was missing was the philosophical glue, someone who could take all of this and articulate clearly, rigorously, without mysticism, exactly what it meant about the nature of time and causation. That someone was Hugh Price. Price was born on May 17, 1953, in Oxford. He studied at Cambridge under Hugh Mellor, a philosopher of science, and went on to hold positions at the University of Sydney, where he founded the Centre for Time, and at Cambridge, where he served as Bertrand Russell Professor of Philosophy at Trinity College from 2011 to 2020. Price is not a physicist, he's a philosopher. But he's the kind of philosopher who reads the physics papers, does the math, and then tells the physicists what their own equations are saying. In 1996, Price published a book called Time's Arrow and Archimedes' Point. The title is important. Archimedes said, "Give me a lever and a place to stand, and I will move the earth." Price's argument was that to understand time, you need a place to stand outside of time, an Archimedean point, a perspective that isn't trapped inside the flow of events from past to future, a view from nowhere, or rather, from no one. And from that perspective, Price argued, the arrow of time looks very different. From inside time, causes obviously come before effects. That's what cause means to us. But from outside time, looking at the block of space-time as a whole, there is nothing obvious about it. The laws of physics are time-symmetric. The equations don't know which way is forward. The asymmetry we perceive, the feeling that the past is fixed and the future is open, is not a feature of fundamental physics. It's a feature of us, of our perspective, of the fact that we are creatures embedded in time, with memories of the past and uncertainty about the future. Price didn't argue that retrocausality is proven. He argued something more subtle. He argued that rejecting retrocausality without good reason is a kind of temporal chauvinism, a prejudice in favor of one direction of time that has no basis in the underlying physics. If you accept that quantum theory is realistic, that the quantum state describes something physically real, and if you accept that the fundamental laws are time-symmetric, then you should expect retrocausal influences, not because the experiments demand it, though they're consistent with it, but because the alternative, accepting a deep asymmetry in time that your own equations don't contain, is the less rational position. In 2017, Price and physicist Matthew Leifer published a paper in the Proceedings of the Royal Society A that made this argument mathematically precise. They showed that if quantum theory is time-symmetric and the quantum state is ontic, meaning physically real, then retrocausality is not just possible, it's unavoidable. Any attempt to keep time symmetry while rejecting retrocausality leads to contradiction. The Leifer-Pusey theorem, as it's become known, was a watershed. It transformed the retrocausality debate from could the future influence the past to given what we know about quantum mechanics, how could it not? And that brings us to the hardest part of this entire story. Not the experiments, not the math, not the interpretations. The hard part is what all of this means. About time, about causation, about whether the future exists, about whether your choices matter, about whether the past you remember is the whole past, or just the part you've been allowed to see. Because if the retrocausalists are right, the answer to that last question is no. The past you remember is not the whole past. There are aspects of the past that were written by events that haven't happened yet, events that you will cause, events that you will choose, and that changes everything. Let's start with the question that every physicist working on retrocausality eventually has to confront. Does the future exist? Not, will the future exist? Does it exist? Right now? Already? Is tomorrow as real as yesterday? Is next year sitting out there, fully formed, waiting for you to arrive? Because retrocausality requires a specific answer. If the future is going to reach back and shape the past, the future has to be there to do the reaching. You can't be influenced by something that doesn't exist yet. So either the future is real, in which case retrocausality makes sense, or the future is not real, in which case retrocausality is dead on arrival, no matter what the experiments say. This isn't a new question. Physicists and philosophers have been fighting about it for over a century. And the physicist who had the clearest answer was Albert Einstein. Most people know Einstein for relativity, for E equals mc squared, for the photoelectric effect that won him the Nobel Prize. Fewer people know that Einstein had a deeply considered position on the nature of time itself. And that position was radical. Einstein believed the future already exists. This follows from special relativity, and the argument is surprisingly simple. Imagine two people, Alice and Bob, moving relative to each other. According to special relativity, they disagree about which events are simultaneous. Events that Alice says are happening right now are, from Bob's perspective, in Alice's future or her past. There is no objective, universal now. No cosmic clock ticking off a single present moment that everyone shares. If Alice's now includes an event that is in Bob's future, and Bob's now includes an event that is in Alice's past, then the distinction between past, present, and future cannot be objective. It's perspectival. It depends on how you're moving. And if the distinction isn't objective, if the future is already there from someone else's reference frame, then in what sense is the future less real than the past? The answer for Einstein was that it isn't. Past, present, and future are all equally real. They coexist. The universe is a four-dimensional block of space-time, laid out in its entirety, with all moments, all events, all histories existing together. We experience time as flowing because we're embedded in the block, experiencing it slice by slice. But the flow is an illusion, a feature of consciousness, not of physics. This is called the block universe, or eternalism, or, if you're feeling dramatic, the view from eternity. Einstein wrote about this explicitly in one of the most moving letters in the history of science. In March 1955, his lifelong friend, Michel Besso, died. Einstein wrote to Besso's family, and in the letter, he said this: "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." Einstein himself died 26 days later. A stubbornly persistent illusion. That's how the greatest physicist since Newton described the flow of time. Not as a discovery, not as a theory, as a fact that follows from the physics he had already proven. Now, not every physicist agrees with Einstein on this. The block universe has critics, but it has one enormous advantage when it comes to retrocausality. In a block universe, the future is real. It's already there. And if it's already there, then it can exert influence on the past without any logical contradiction. You don't need the future to send a message backward. Both the future and the past exist simultaneously, and the correlations between them are just features of the block, patterns in the four-dimensional structure of space-time. Ken Wharton, a physicist at San Jose State University, who has become one of the leading advocates of retrocausal models, makes this point explicitly. His approach treats the universe as a boundary value problem. In standard physics, you specify initial conditions, the state of everything at one moment, and then evolve the equations forward to predict the future. Wharton says you should specify boundary conditions at both ends, initial conditions in the past and final conditions in the future. The physics in between is determined by both, simultaneously, like a bridge anchored at both ends. He calls these all-at-once models. Nothing evolves forward in time. Nothing evolves backward in time. The entire four-dimensional history is solved as a single mathematical problem, with constraints from both past and future shaping everything in between. The result is a universe that looks retrocausal from our forward-in-time perspective, but from the perspective of the block, it's just consistent. Everything fits together. Both ends of the bridge hold. Wharton characterizes his models as retrocausal, but not retro-signaling. The future constrains the past, but those constraints can never be exploited to send information backward. The reason is the same reason Aharonov gave. Quantum uncertainty hides the future's influence in statistical noise. You can see it in patterns. You can see it in weak values. You can see it in Bell correlations, but you can never see it in any single event, which means you can never use it to create a paradox. This is the Novikov self-consistency principle in action. Igor Novikov, a Russian physicist, demonstrated in the 1980s and 90s that retrocausal physics doesn't have to create paradoxes. His principle states that the only solutions to the laws of physics that can occur in the real universe are those that are globally self-consistent. No grandfather paradoxes, no logical contradictions. Just a universe where everything fits from beginning to end, like a completed jigsaw puzzle that was always going to look the way it looks. Novikov proved this with billiard ball thought experiments involving wormholes. A ball enters a wormhole, exits in the past, and collides with its earlier self. You'd think this creates an infinite loop or a contradiction, but Novikov showed that self-consistent trajectories always exist. The ball nudges its earlier self at just the right angle, which sends that earlier self into the wormhole at just the right trajectory, which produces the nudge at exactly the right angle. The loop closes cleanly. Physics is satisfied. Causality runs in a circle, but the circle is never broken. All of this might sound abstract. Block universes and boundary value problems and self-consistent loops. So let me try to make it concrete. Let me try to explain what it would feel like to live in a retrocausal universe. And the answer is, it would feel exactly like this, exactly like the universe you already live in. You would wake up in the morning, you would make choices, coffee or tea, left turn or right turn, this job or that job. Those choices would feel free. They would be free, in every meaningful sense. No one predetermined them. No cosmic script dictated them. But those choices, once made, would have consequences that reach in both directions. Forward into the future, which is obvious and familiar, and backward into the past, which is hidden and strange. Not backward in a way you could detect. Not backward in a way that changes your memories or rewrites your history in any observable way, but backward in a way that adjusts the quantum-level hidden variables of particles you interacted with before you made the choice. Backward in a way that creates the correlations Bell's theorem says must exist. Backward in a way that writes the invisible ink Aharonov describes. The ink that only becomes legible when someone gathers enough statistics and looks at the patterns. You would never notice. You can't notice. That's the whole point. The retrocausal influences are real, but they're hidden behind quantum uncertainty, buried in statistical noise, protected by the no communication theorem. They shape the deep structure of reality without ever disturbing the surface. It's like living in a house where someone rearranges the furniture every night while you sleep, but always puts everything back in a position that's consistent with where you left it. You'd never catch them. You'd never notice anything wrong. But the arrangement you see in the morning isn't entirely the arrangement you left last night. Something has been adjusted. Something has been touched by a hand reaching from a direction you can't see. Is that terrifying? I think it depends on what you find terrifying. If what scares you is the idea that you don't have free will, retrocausality is actually reassuring. Unlike superdeterminism, which says every choice you've ever made was hard-coded at the Big Bang, retrocausality preserves genuine freedom. You choose. The universe adjusts. Your choices matter so much that they echo backward through time, reshaping the conditions that led to the moment of choosing. But if what scares you is the idea that the past isn't what you think it is, then yes, retrocausality is terrifying because it means the past isn't finished. It means history, at the quantum level, is not a closed book. It's a living document, continuously edited by events that haven't happened yet, by choices not yet made, by a future that is just as real and just as present as the moment you're in right now. And that brings us to the deepest disagreement in all of physics. Not about particles or fields or forces, about time itself, about whether the thing you experience as the flow of time, the thing that makes you feel like you're moving from past to future, from birth to death, from one moment to the next, whether that thing is real. There are three positions, and all three of them are held by serious, credentialed physicists who have spent their careers thinking about this. The first position belongs to Carlo Rovelli. Rovelli is an Italian physicist, co-developer of loop quantum gravity, based at Aix-Marseille University, and the author of a best-selling book called The Order of Time. His position is simple, elegant, and devastating. Time does not exist. Not time is an illusion in some poetic sense. Time is not a fundamental feature of reality. The Wheeler-DeWitt equation, which describes quantum gravity, contains no time variable. There is no taha. The most fundamental equation we have for the structure of space-time does not include time as an ingredient. Rovelli argues that time is merely a perspective. It arises from biology, from evolution, from the fact that we are macroscopic creatures with memories and expectations, interacting with the universe in a blurred, thermodynamic way. We see entropy increasing. We remember the past, but not the future. And from these asymmetries in our experience, we construct the feeling of time flowing. But the feeling is ours, not the universe's. At the deepest level, Rovelli says, the universe is made up of networks of relationships, not of things evolving through time. He writes that this distinction between past and future is not present in the basic grammar of the world. It comes about only because we have a blurred vision of reality. If Ravelli is right, then retrocausality isn't even the right word. You can't have backward causation if there's no forward and backward. There's just the structure, the block, the pattern. And what we call retrocausal influences are just features of that pattern that look strange from our time-bound perspective, but are perfectly natural from the timeless perspective of the equations. The second position belongs to Julian Barbour. Barbour is an independent British physicist who has spent his career outside the university system, working from a farmhouse in Oxfordshire. He published a book in 1999 called The End of Time, and it proposed something even more radical than Ravelli's view. Barbour doesn't just say time doesn't flow. He says there are no moments, no succession of instants, no before and after. Instead, there is what he calls Platonia, a timeless arena of all possible configurations of the universe. Every possible arrangement of every particle, every possible state of every field exists as a point in Platonia. And that's all there is. Points in a configuration space. What about your memories? What about the feeling that 5 minutes ago is different from right now? Barbour calls these time capsules, structures in the present configuration of the universe, like the arrangement of neurons in your brain that contain records of what appear to be past events. But those records don't prove the past happened. They just prove that the present configuration contains structures that look like memories. As Barbour puts it, the only evidence you have of last week is your memory. But memory comes from a stable structure of neurons in your brain now. This is profoundly unsettling. It means the past, as you remember it, might not have happened. Not in the sense that your memories are wrong, in the sense that there is no past for them to be memories of. There is only the present, arranged in a way that creates the appearance of history. If Barbour is right, retrocausality is meaningless. Not because it's wrong, but because there's no retro. There's no time for causes to be backward in. And the third position belongs to Lee Smolin. Smolin is a founding faculty member of the Perimeter Institute in Waterloo, Canada, and he argues the exact opposite of Ravelli and Barbour. Time is real. Time is fundamental. Time is the most real thing there is. Smolin published Time Reborn in 2013, and his argument is that physicists have made a catastrophic error. They have confused their mathematical models, which are timeless, with reality, which is not. The equations of physics are written on paper. Paper doesn't experience time, but the universe does. The universe is happening. Processes are occurring. Things are changing. And that change is not reducible to a static mathematical structure. Smolin even proposes that the laws of physics themselves might evolve over time, that the constants of nature, the strengths of forces, the masses of particles might not be eternal. They might change. They might have been different in the past. They might be different in the future. Time, for Smolin, is not the stage on which physics plays out. It is the deepest feature of reality itself. He wrote that he used to think his job as a theoretical physicist was to find the eternal, timeless law that governs everything. And then he realized that this faith in an eternal law was itself a kind of mysticism, a religious conviction dressed up as science. If Smolin is right, then retrocausality is genuinely backward causation. Effects genuinely precede causes in a real, flowing time. And that's unsettling for a different reason. Because if time is real, and the future can influence the past, then the flow you feel, the sense of moving from moment to moment, is not just a ride, it's a negotiation. Between what has been and what will be. Between memory and destiny. 3 physicists, 3 positions. Time doesn't exist. Time doesn't have moments. Time is the most fundamental thing there is. And all 3 are consistent with the experimental evidence for retrocausality. That should bother you. Not because one of them must be wrong, though at most one can be completely right, but because the question, what is time, remains genuinely open. After a century of relativity, after 8 decades of quantum mechanics, after everything we've measured and tested and proven, we still don't know what time is. We know the equations, we know the predictions, we know the experiments work. We do not know what time is. And retrocausality lives in that gap, in the space between what we can calculate and what we can understand. So where does this leave us? Let me try to be honest about what we know and what we don't. We know that Bell's inequality is violated. That's not a theory. It's an experimental fact, confirmed to over 100 standard deviations across dozens of independent laboratories on every continent. The universe is not locally realistic. Something weird is going on. We know that delayed choice experiments work exactly as quantum mechanics predicts. The past, at the quantum level, does not have definite properties until a measurement pins them down. And that measurement can happen after the fact. We know that entanglement swapping can create correlations between particles that never interacted, based on a choice made after those particles have already been detected and destroyed. The statistical evidence is clear. We know that the two-state vector formalism and the transactional interpretation are mathematically rigorous frameworks that reproduce all the predictions of standard quantum mechanics while treating the future as a genuine contributor to present physics. They're not fringe. They're published in top journals. They make testable predictions that have been confirmed. We know that the Leifer-Pusey theorem establishes that if quantum theory is time-symmetric and realistic, retrocausality follows. Not might follow. Follows. What we don't know is whether quantum theory is realistic, whether the quantum state describes something physically real, or just our knowledge of reality. That's the interpretive question that has divided physicists since 1927, and it shows no sign of being settled anytime soon. If you're a realist, if you think the quantum state is real, then retrocausality is the most natural, most parsimonious explanation for quantum non-locality. It preserves locality. It's compatible with relativity. It doesn't require parallel universes or consciousness-dependent collapse or cosmic conspiracies stretching back to the Big Bang. If you're not a realist, if you think quantum mechanics is just a tool for making predictions and doesn't describe reality directly, then retrocausality is optional. Interesting. Mathematically valid, but not compelled. Most working physicists will tell you they don't think about interpretations. Shut up and calculate. The equations work. Why worry about what they mean? But here's the thing. The equations keep pointing in the same direction. The time symmetry of the fundamental laws. the violations of Bell's inequality, the delayed choice results, the weak value experiments, the entanglement swapping. Every time we look more carefully at the structure of quantum mechanics, we find more evidence that the distinction between past and the future is not what we assumed. Maybe that's a coincidence. Maybe all of these results have perfectly mundane explanations that don't involve the future influencing the past. Maybe we'll find a way to interpret quantum mechanics that preserves common sense causation and doesn't require us to rethink our most basic assumptions about time. Or maybe the universe has been trying to tell us something for 100 years, and we've been too stubborn to listen. John Wheeler spent his last decades saying the universe is stranger than we imagine, and possibly stranger than we can imagine. He said that behind it all is surely an idea so simple, so beautiful, that when we grasp it, in a decade, a century, or a millennium, we will all say to each other, how could it have been otherwise? Maybe that idea is retrocausality. Maybe the universe is simpler than we think. And the price of that simplicity is accepting that time isn't a river flowing in one direction. Maybe it's more like an ocean, with currents running in every direction, and we're just fish who've spent our whole lives swimming one way and assumed that was the only way to swim. Yakir Aharonov, 93 years old and still publishing papers, says the future is already reaching back, that there are aspects of the present that only make sense if you know what's coming. The two particles can be identical in every forward-looking way, but secretly different because their futures are different. John Cramer, 91 years old, says the universe is a handshake, an offer wave going forward, a confirmation wave coming back, a transaction, a conversation between what was and what will be. Hugh Price says we suffer from temporal chauvinism, that we privilege one direction of time simply because we happen to live in it. That from the outside, from the Archimedean point, there is no privilege. There is just structure, pattern, the block. And Bell, who started all of this, who died too young to see his work recognized, who worked on quantum foundations as a hobby because the physics establishment said it wasn't real science, Bell saw the implications more clearly than anyone. He said there is a way to escape spooky action at a distance, but it involves absolute determinism, the complete absence of free will. Or, he might have added, it involves accepting that time doesn't work the way you think it does. Wheeler's great smoky dragon hangs in the air, sharp at the tail where the photon begins, sharp at the mouth, where the detector clicks, and in between, smoke, impenetrable, irreducible smoke. We have no right to say what the dragon looks like in between. We have no right to say whether the cause came before the effect, or the effect came before the cause. We have no right to say whether the past made the future, or the future made the past. All we have are the two sharp points, the beginning and the end, the preparation and the measurement, the question and the answer, and the growing, uncomfortable suspicion that the answer might have been there before the question was ever asked. Einstein said the distinction between past, present, and future is a stubbornly persistent illusion. He wrote those words 4 weeks before his own death, about a friend who had already died. People like us, who believe in physics, know this. He was writing to comfort a grieving family, but maybe he was also stating a physical fact. Maybe Michel Berceau didn't go somewhere Einstein couldn't follow. Maybe they're both still there, in the block, in the pattern, in the completed puzzle that was never really assembled piece by piece, but existed all at once, from the very beginning, or from the very end. In physics, those might be the same thing. There's one more thing I want to leave you with, because I think it's the detail that makes all of this feel real instead of abstract. In 2023, a team at ETH Zurich in Switzerland published a paper in Nature that might be the most impressive Bell test ever conducted. They didn't use photons, they used superconducting circuits, macroscopic objects cooled to near absolute zero, separated by 30 meters. These aren't atoms. These aren't subatomic particles. These are things you can see with your eyes, wired into a circuit board, behaving in ways that violate Bell's inequality. Their CHSHS value was 2.0747, plus or minus 0.0033, above the classical limit of 2. The p-value was less than 10 to the negative 108th power. Let me put that number in perspective. A p-value tells you the probability of getting your result by pure chance. The standard threshold for a scientific discovery is a p-value of 0.05, which means a 5% chance of a fluke. The Higgs boson was announced at a p-value of about 3 in 10 million. The Bell test in 2015 had a p-value of about 3.7 times 10 to the negative 31st power, which I described earlier as requiring more trials than there are atoms in the visible universe to produce by accident. The ETH Zurich result has a p-value with 108 zeros after the decimal point. There is no analogy that makes this number intuitive. It is, for all practical purposes, certainty. The universe violates Bell's inequality. Period. End of discussion. Whatever explanation you favor, whether it's non-locality, many worlds, retrocausality, or something nobody has thought of yet, it must account for this fact. And in the same year, another team published a result on something called the delayed choice quantum Cheshire cat. Using neutron interferometry, they spatially separated a neutron from its spin. The particle went one way, its property went another way, like the Cheshire cat from Alice in Wonderland, whose grin remains after the cat has vanished, and the assignment of which path the neutron took depended on a delayed choice, made after the neutron had already passed through the interferometer. These experiments keep getting more precise, more dramatic, and more difficult to explain with any framework that insists on a simple forward flow of time. The same year, 2023, also saw tests of the Leggett-Garg inequality, sometimes called the temporal Bell inequality, where Bell's original inequality tests, whether distant particles can have predetermined properties, the Leggett-Garg inequality tests, whether a single system can have definite properties at all times, even when you're not looking. It tests what physicists call macro-realism, the common sense view that big objects always have definite states. Previous experiments with superconducting qubits had already violated the Leggett-Garg inequality by 77 standard deviations over timescales of just 9 nanoseconds. The universe doesn't just violate our assumptions about space, it violates our assumptions about time, not just for photons, not just for electrons, for macroscopic quantum systems that you can hold in your hand. The experiments are not ambiguous. The statistics are not marginal. The evidence is not emerging. It has emerged. The question is no longer whether quantum mechanics violates our intuitions about time and causation. The question is what we're going to do about it. I keep coming back to Wheeler's brother, Joe Wheeler, fighting in Italy, sending a postcard with 2 words, "Hurry up," and John Archibald Wheeler, working on the bomb, feeling for the rest of his life that if time had been arranged differently, if the sequence of events had broken another way, his brother would have lived. Wheeler spent his career asking whether the past is real, whether the sequence matters, whether the observer participates in creating reality, and I don't think you can separate those questions from the grief of a man who lost his brother to timing, to the brute fact that events happen in an order, and that order has consequences, and sometimes those consequences are permanent. But what if they're not? Not permanently permanent, anyway. What if the order is less fixed than Wheeler feared? What if the sequence is not a prison but a perspective? What if the past really is, as the two-state vector formalism suggests, shaped by a future that hasn't arrived yet? That's not comfort. Not exactly. Retrocausality doesn't mean you can go back and change things. It doesn't mean the war could have ended differently. It doesn't mean Joe Wheeler could have survived, but it might mean that the past, as we understand it, is not the whole story. That there are aspects of what happened, aspects of every event in history that are still being determined, still being written, by choices that haven't been made yet, by measurements not yet taken, by a future that is, in some sense, reaching back right now and filling in details we never knew were missing. Is that comforting or terrifying? I honestly don't know. I think it depends on whether you trust the universe to be self-consistent. Novikov says it always is. The loop always closes. The puzzle always fits. No paradoxes, no contradictions. Just a reality that's more complex, more interconnected, and more strange than we ever imagined. Richard Feynman said that nobody understands quantum mechanics. He was right when he said it in the 1960s. And he may still be right today. But understanding is a spectrum, not a switch. We understand more than we did. We understand that Bell's inequality is violated. We understand that delayed choice works. We understand that time-symmetric quantum mechanics is mathematically rigorous. We understand that the future, in some well-defined, experimentally supported sense, participates in shaping the present. We just don't understand what that means yet. But here's one last thought. Feynman described quantum mechanics as absurd from the point of view of common sense, but fully in agreement with experiment. He said he hoped we could accept nature as she is. Absurd. Maybe absurd isn't the right word anymore. Maybe the universe isn't absurd. Maybe it's just bigger than we thought. Bigger in time, not just in space. Reaching in directions we can't point to. Shaped by events we haven't chosen yet. And maybe the most terrifying thing about retrocausality isn't that the future influences the past. Maybe the most terrifying thing is that we've been living with it all along and never noticed. Wheeler said that behind it all is surely an idea so simple, so beautiful, that when we finally grasp it, we will all say to each other, how could it have been otherwise? He died in 2008. The loophole-free Bell test came 7 years later. The Nobel Prize for Entanglement came 14 years later. The ETH Zurich result, with its impossible p-value, came 15 years later. Wheeler never saw any of it, but if the retrocausalists are right, maybe that doesn't matter as much as we think. Maybe the distinction between what Wheeler saw and what Wheeler didn't see is less sharp than it appears. Maybe the boundary between the observed and the unobserved, between the remembered and the yet to come, is not a wall but a membrane, porous, permeable, thin enough that the future leaks through. The smoky dragon hangs in the darkness, tail sharp, mouth sharp, body hidden, and somewhere in that smoke, in the quantum fog between preparation and measurement, between the birth of a photon and its death in a detector, the future and the past are doing something we don't have a name for yet. Something that isn't quite causation, something that isn't quite correlation, something that the equations describe perfectly, but the language hasn't caught up to. We'll find the word eventually. We always do. Until then, the experiments keep running. The correlations keep violating the inequality. The future keeps reaching back. And the great smoky dragon keeps its secrets. For now.